Hello and welcome back, fellow path integrators. Today with a very special topic, spirals, or to be more specific, we're going to calculate the length of an infinite spiral, of an infinite logarithmic spiral. And you won't believe the solution. It is absolutely amazing. It kind of blew my mind when I saw it, the connections that I could see that mathematics is creating. And the cool thing about spirals is they appear everywhere in nature. Like, you can find them in the formation of clouds, in hurricanes, for example, or you can find them in spiral galaxies, or you can find them even in the shell of a snail. So spirals are everywhere. Spirals are part of nature. And this is why I thought you should make a video about this. So what we're going to do is we're going to take a look at a very simple logarithmic spiral with the following parametrization. So we have gamma, which is defined on the interval from 0 to infinity, and the whole thing maps onto r squared because our spiral will be in the two-dimensional plane, and the parametrization itself will be dependent on the parameter t, and we have an x and a y coordinate, so we have a two-dimensional vector, and it will be e to the power of minus t times cosine of t and e to the power of minus t times sine of t. So now you might ask yourself, why is this called a logarithmic spiral? Well, therefore you have to remember how the parametrization of a circle looks like. So let's take a look at the parametrization of a circle, which is r times cosine of t for the x coordinate and r times sine of t for the y coordinate. And since our spiral looks a lot like a circle with a decreasing radius, we can identify the factor e to the power of minus t with the decreasing radius of our spiral. So what we will have is, let's change the color again, that r of t is e to the power of minus t. And if we express the parameter t dependent on the radius r, which is decreasing, then we will get a logarithm. So we will have t will be the natural log of 1 divided by r. And this is why it's called a logarithmic spiral. So now let's go back to the original task to calculate the length of that infinite ongoing logarithmic spiral. And therefore we're going to take a look at an integral once again. So the integral goes from 0 to infinity, because this is our parameter space up here, from 0 to infinity, and we will integrate over the norm of the derivative of gamma of t, and of course we have a dt. So what is the norm of a function or a vector? So if we have a function and we want the norm of this, then we are going to take the square root of the scalar product with itself. So you know that scalar products not only can be defined for vectors, but you can define them for functions as well. Or to be more precise, you can define a scalar product for the elements of a vector space, and functions can be elements of a vector space as well. For example, in quantum mechanics you often have functions which form a vector space. So this is why we can also say the scalar product is defined for a function. So if we take a look at the norm of the derivative of gamma of t, then the whole thing will look like this. So we have the norm of the derivative of gamma of t, which is the square root of the scalar product of the derivative of gamma with itself. So seeing this, we know what we have to do. First, we need to calculate the derivative of our parametrization here. Then we need to calculate the scalar product with itself, and then we take the square root out of that. So let's do that. First, we tackle the derivative. So the derivative of gamma is, so let's write d over dt, and then we copy this thing here down here. Yeah, let's put that a little bit more down so it looks not so stacked up, a little bit more space. So what we're gonna do now is we're going to apply the product rule. So what we will get, this is already too stacked up again. So what we will get then is minus e to the power of minus t times cosine of t. So the cosine remains unchanged, and then we have minus e to the power of minus t times sine of t, because the derivative of the cosine is minus the sine of t. So now let's take a look at the y-coordinate. For the y-coordinate we have minus e to the power of minus t times sine of t this time, and now we have a plus e to the power of minus t times cosine of t. Alright, so this is our derivative of the parametrization. Now we just need to take the scalar product with itself. So what we can do first is we can extract the e to the power of minus t out of the integral, or the minus e to the power of minus t. So let's first rewrite the whole thing. We have minus e to the power of minus t times, so here we have cosine of t, and here we have plus sine of t. So, and then in the y-coordinate we have sine of t, and since we are extracting minus e to the power of minus t, we will get a minus here, so we have minus cosine of t. So, in order to calculate the scalar product, we need to calculate this with, multiply this with itself. So let's copy that once again and put it next to each other. So we have like times, and let's put a bracket on here so we are not getting confused with the minus. So we have minus and minus that will cancel each other out, so we can already put that away. So we don't need that, and let's put the e to the power of minus t here. And yeah, the eraser is a bit too big. So yeah, well, I'm going backwards, I'm sorry for that. So we have this scalar product of the derivative with itself is this whole thing here. So we have e to the power of minus t times e to the power of minus t, so what we will get is e to the power of minus 2t, and then we will get a big bracket where we write cosine of t plus sine of t squared plus, and now we do this, the y-coordinate with itself, and we will get sine of t minus cosine of t squared. And now we apply the binomial formula, which is quite simple. So we have e to the power of minus t times cosine squared of t plus sine squared of t plus 2 sine t cosine of t, and now plus the second binomial formula, which is this one. So we have sine squared of t plus cosine squared of t minus 2 times sine of t times cosine of t, and close the brackets. Alright, so cool thing here is this and this cancels each other out, and we have a beautiful relationship between cosine squared and sine squared, because here we have cosine squared plus sine squared, which is 1, and here we have sine squared plus cosine squared, which is also 1, and this will leave us with the eventual result of 2 times e to the power of minus 2t. So this is the scalar product of the derivative of the parametrization with itself. To get the norm, we now have to simply take the square root out of that. So this norm of the derivative of the parametrization is the square root of 2 times e to the power of minus t. And this is what we're going to plug in into our integral. So let's do that. So we have the length of our curve, of our spiral, is the integral from 0 to infinity over the norm of the derivative of the parametrization times dt, our integration variable. And now we plug that in, we plug this in, so we get the 0 to infinity of square root of 2 times e to the power of minus t times dt. And we can extract the square root of 2 out of the integral because it is just a constant. So we have square root of 2 times the integral from 0 to infinity e to the power of minus t dt. What we will do now is we will put a parameter a into the integral instead of the infinity, and then we will calculate the limes of this function that we will get. So what we do is square root of 2 times the limes of a going to infinity times the integral from 0, this time not to infinity, to a of e to the power of minus t dt. And this is quite simple, because what we have to do is just we need the stem function of e to the power of minus t. So we have square root of 2 times the limes of a going to infinity. And now we have minus e to the power of minus a, and then minus e to the power of minus 0. So this is also quite simple, because this gives us a plus, and e to the power of minus 0 is 1, and we will have simply the limes of a going to infinity of e to the power of minus e plus limes of a going to infinity of 1. So this of course is 1, and this of course is 0. So the only thing that we are left with is the square root of 2, and this is the solution to our integral. So the logarithmic spiral, the simple logarithmic spiral that we defined above, has a length of square root of 2, and I think that is absolutely amazing. Like, you have the only even prime number, take the square root out of it, get an irrational number, and that is the solution to your logarithmic infinite spiral, a geometric shape that appears everywhere in nature. So, well, from here on we could philosophize a little bit about the connections of irrational numbers and spirals and galaxies and cloud formations to the whole nature of the universe. So let's just do that in the comments. And let me also know how you found that video. If you found it nice, if you liked hanging out with me today and solving this integral, please leave a like. Subscribe to my channel, that helps me a lot with the logarithm, not the logarithm, I'm sorry, with the algorithm. Yes. So, yeah, it was fun, and see you in the comments and in the next video. Bye!